In 1926, a French farmer walked into a patent office with plans that would terrify every fertilizer company on Earth. His invention? A copper wire. That's it. No chemicals, no engines, no complexity. Just strategically placed copper wire that he claimed could triple harvests. British government officials documented the results. 10-foot corn stalks, pumpkins the size of prize hogs, vegetables that seemed physically impossible. Then, the evidence vanished. The technology was buried. And for nearly 100 years, you've been paying for fertilizer you might never have needed. Today, we're digging up what they tried to erase. Right now, the global fertilizer industry generates over $200 billion annually. Every single growing season, farmers worldwide write another check to the same corporations that convinced us there's no alternative. It's the perfect business model, a product you must repurchase forever or your crops fail. But here's what doesn't make sense. In the 1920s, a French experimenter named Justin Christofleau was growing record-breaking harvests using nothing but copper wire and atmospheric electricity. Government committees investigated. Scientists documented it. Patents detailed the exact specifications. The results were photographed, measured, and verified. Then, just as synthetic fertilizers hit the market, this technology mysteriously disappeared from scientific literature. Coincidence? Let's find out what really happened and why this forgotten method might be more relevant in 2026 than ever before. Justin Christofleau wasn't a university professor or a corporate scientist. Born in France in 1865, he was a farmer who became obsessed with a question that would consume his entire life. What if plants needed more than just soil nutrients? While his neighbors focused on traditional farming methods, Christofleau noticed something nobody else was paying attention to. He observed that plants seemed to grow differently depending on their position in a field, even when soil quality was identical. Some areas consistently produced healthier crops. Others lagged behind. The difference couldn't be explained by soil chemistry alone. This observation led him down a path that would make him either a genius or a madman, depending on who you asked. Christofleau became convinced that plants were responding to invisible electrical forces flowing between the sky and the earth. For decades, he built strange apparatus in his fields: metal rods, copper spirals, elaborate antenna systems. His neighbors thought he'd lost his mind. But the results in his experimental gardens told a different story. By the early 1920s, reports from his farm were attracting attention across Europe. Visitors claimed to see oats growing to 5 feet tall. Ancient fruit trees that had stopped producing suddenly burst back to life. The vegetables were genuinely abnormal in size. On October 26, 1925, Christofleau made his work official. He filed patent CH111 8648A in Switzerland for what he called the electromagnetic telluric celestial apparatus. This wasn't some vague concept scribbled on a napkin. The patent document, which still exists in Swiss archives today, specified every component: copper plates, magnetic steel elements, precise wire gauges, exact positioning requirements. It was a complete blueprint for capturing atmospheric electricity and channeling it directly into crop root zones. Christofleau published his findings openly in agricultural journals and books. He invited scientists, skeptics, and journalists to visit his experimental gardens. He wanted scrutiny. He wanted verification. He believed he'd discovered something fundamental about how plants actually function, and he wanted the world to know. For a brief moment, it looked like he might succeed. The photographs from this era are genuinely startling. We're talking about cabbages that reached nearly waist height, pumpkins requiring 2 people to lift, root vegetables that looked like they'd been grown on another planet with different physics. These weren't manipulated images. Photography in the 1920s didn't allow for the kind of digital fakery we're used to today. These were actual photographic prints published in French gardening magazines and local newspapers, often accompanied by eyewitness testimonials from visitors who'd seen the crops firsthand. But Christofleau wasn't alone. Across Europe, Farmers and experimenters were installing similar systems and reporting comparable results. The phenomenon was widespread enough that it caught the attention of the British government. In 1918, the British Ministry of Agriculture established the Electroculture Committee with a specific mandate: investigate these electrical farming claims and determine what was real. For 18 years, from 1918 to 1936, this official government committee traveled across Europe, visited experimental farms, collected photographs, documented yield measurements, and interviewed dozens of farmers using electrical methods. Their interim reports, many stamped "not for publication," filled thousands of pages. They cataloged case after case of extraordinary crop yields: giant barley, massive root vegetables, yields sometimes doubling or tripling compared to conventional methods. The committee didn't dismiss this as fraud. They documented it systematically, treating it as a legitimate phenomenon requiring explanation. Yet here's the mystery. Despite nearly 2 decades of investigation and mounting documentation, these findings never translated into widespread adoption. The committee's reports were archived. The photographs gathered dust. And within another decade, electroculture had been almost completely erased from mainstream agricultural science. Something happened between the documentation and the dissemination. To understand what, we need to understand the science these farmers had stumbled onto. Right now, as you watch this, you're sitting in an electrical field. You can't feel it, but it's measurable, predictable, and constant. Scientists call it the atmospheric potential gradient, and it exists everywhere on Earth's surface. The sky holds a positive electrical charge. The ground beneath your feet holds a negative charge. Between them flows a voltage gradient of approximately 100 volts for every meter of altitude. This isn't lightning or static shock. It's a gentle, constant electrical potential difference that never stops. Here's what makes this fascinating. Plants exist right in the middle of this field. They're not passive objects sitting in soil. They're active participants in an electrical system. Look at a plant under a microscope and you'll see its surfaces covered in microscopic structures. Tiny hairs, wax crystals, irregular textures. These aren't random. They function as electrical interfaces. The leaves and stems collect atmospheric charge. The roots, buried in the negatively charged earth, complete the circuit. Every plant is essentially a living antenna, continuously exchanging electrical energy between sky and soil. This isn't theoretical. Scientists have measured it. Insert fine electrodes into a plant and the surrounding soil, and you can detect tiny electrical currents flowing through the plant's tissues. These aren't random fluctuations. They're organized signals called action potentials and variation potentials, traveling through the plant at measurable speeds. When a tomato leaf gets damaged by an insect, for example, an electrical signal races through the stem within seconds, triggering defensive chemical production in leaves nowhere near the injury. The plant is using electricity for instant, whole-organism communication. It's a sophisticated biological circuit that's been operating for hundreds of millions of years. Modern research has revealed that these electrical signals do far more than transmit alerts. They regulate photosynthesis rates. They control growth hormones. They influence how efficiently plants absorb nutrients, developed to manufacture explosives for World War I, had been adapted for peacetime use, mass-producing synthetic ammonia for fertilizer. Between 1920 and 1960, global synthetic fertilizer production exploded from roughly 1 million tons annually to nearly 20 million tons. Factories in Germany and the United States operated around the clock. As production scaled, prices plummeted from about $100 per ton to under $30 per ton, making chemical fertilizers accessible to farmers worldwide. But the brilliant innovation wasn't the chemistry. It was the economics. Unlike a copper wire that could last decades with zero maintenance, chemical fertilizers must be repurchased every single growing season. Spring arrives, farmers buy fertilizer. Harvest ends. Next spring, they buy again. It's a subscription model disguised as agriculture. Every season generates new revenue. Every harvest creates new dependency. For fertilizer manufacturers, this was a perpetual profit machine. For farmers, it became an inescapable cycle. Try to skip a season, and your yields would drop. Compared to neighbors who kept buying, the economic pressure to continue purchasing was built into the system. Now imagine you're a fertilizer company executive in 1930. Your factories are running at capacity. Your distribution networks span continents. Your quarterly profits are climbing steadily. And then you hear about a French farmer claiming that a few dollars worth of copper wire can produce the same results as your product, permanently, with zero recurring cost. That's not competition. That's an existential crisis. What happened next wasn't a conspiracy in the classic sense. There were no secret meetings or explicit orders to suppress electroculture. It was something more insidious: the gradual, systematic marginalization of an idea through thousands of small decisions that collectively erased it from respectable discourse. Agricultural journals, many dependent on fertilizer company advertising revenue, began framing electroculture as fringe science. University researchers, reliant on industry funding, avoided the topic to protect their careers. Newspaper editors started using dismissive language like miracle claims and unscientific methods when covering electrical farming, often lumping legitimate research with perpetual motion machines and other pseudoscience. Even the British Electroculture Committee's own findings, the result of 18 years of systematic investigation, were stamped not for publication and filed in government archives where most scientists would never see them. By the late 1930s, the conversation had shifted completely. It was no longer about whether electroculture worked. It was about whether serious scientists should even discuss it. The technology wasn't disproven. It was made socially unacceptable. For decades, electroculture remained in the shadows, practiced by a small community of experimenters, but dismissed by mainstream agriculture. Then, something happened that changed everything. Researchers at the Chinese Academy of Agricultural Sciences conducted what may be the largest electroculture trial in human history. The scale was unprecedented: 3,600 hectares, equivalent to more than 6,000 football fields. This wasn't a backyard garden. This was industrial-scale agriculture. They suspended high-voltage wires above vast crop fields, creating an enhanced electrical field similar to what Christofleau had envisioned, but magnified to feed entire cities. No chemical fertilizers, no pesticides, just amplified atmospheric electricity. The results, published in peer-reviewed journals, were extraordinary. Average yield increases of 30% across the trial fields. More wheat, more rice, more vegetables, all grown without synthetic fertilizers. But the yield increase wasn't even the most surprising finding. Pesticide use dropped by 70 to 100% in many areas. Farmers reported dramatic reductions in insect infestations and plant diseases, even in regions where pests had historically required heavy chemical intervention. The plants weren't just bigger. They were healthier, more resilient, naturally resistant to stresses that normally demanded chemical protection. This wasn't anecdotal. This was reproducible data collected across enormous geographical areas over multiple growing seasons, the kind of evidence that makes dismissal difficult. Similar studies in India documented yield increases of 20 to 40% in rice and wheat. European trials showed enhanced growth and improved stress resistance. The evidence base is growing, and it's becoming increasingly hard to ignore. What makes these modern studies particularly compelling is that they're documenting the underlying mechanisms. Advanced imaging shows plants exposed to enhanced electrical fields exhibit increased photosynthesis, enhanced nutrient uptake, elevated antioxidant production, and improved water efficiency. We're finally understanding how this works at the cellular level. Now, before anyone rushes out to experiment, we need to establish a critical distinction. There are two completely different approaches to electroculture, and confusing them could be dangerous. The large-scale studies use powered systems. High-voltage electricity run through suspended wires using transformers and generators. These create electrical fields measured in thousands of volts. They work, but they require engineering expertise and carry genuine electrical hazards, not suitable for home experimentation. But there's a second approach, the one Christofleau pioneered, that's remarkably simple and completely safe. Passive electroculture. No power source, no batteries, no generators, nothing plugged in. It relies entirely on the natural electrical potential between sky and earth, using copper wire as an antenna to concentrate ambient energy. Here's exactly how to set it up. You need 14-gauge bare copper wire, available at any hardware store for a few dollars. Cut a piece about 3 to 4 feet long, using a wooden dowel roughly 12 to 16 millimeters in diameter. Wrap the wire into a loose spiral with at least 3 complete turns. The spiral diameter should be between 5 and 20 centimeters, with spacing so air and light can pass through. Drive the dowel into the soil so the spiral sits about 10 to 15 centimeters deep, with the top emerging just above the surface. Here's the critical part many people miss. The tip of the spiral must point toward magnetic north, not approximately north, precise magnetic north using a compass. This alignment with Earth's magnetic field lines appears essential for effectiveness. Position your spiral 10 to 20 centimeters from your plant's base. Tomatoes, beans, and squash respond well, but many gardeners report particularly dramatic results with leafy greens. Now here's what separates real experimentation from wishful thinking. Proper methodology. Plant identical crops in similar conditions. Install copper spirals near half, but not the others. Keep everything else identical. Same watering, same sun exposure, same soil. Every 2 weeks, measure height, count leaves, note vigor, document pests, photograph from consistent angles. At harvest, weigh yields separately. One experimenter in Ohio did exactly this with lettuce. Same seeds, same beds, same everything except copper spirals near half the plants. After 12 weeks, 40% yield increase from spiral-enhanced plants, significantly fewer aphids, 0 powdery mildew that had plagued previous seasons. Total investment? Less than $5 in copper wire. 15 minutes setup time. The method is safe, silent, requires 0 maintenance, and it offers a way to personally test whether a century of agricultural orthodoxy might be fundamentally incomplete. Let's zoom out and examine what's actually at stake here. Global fertilizer use now exceeds 185 million tons annually. That's a $200+ billion market, controlled by a handful of multinational corporations. Farmers worldwide are locked into dependency cycles, unable to achieve competitive yields without purchasing chemical inputs season after season. Meanwhile, soil health is declining globally. Decades of intensive fertilizer use have disrupted soil microbiomes, degraded soil structure, and created massive environmental problems. Nutrient runoff poisoning waterways, ocean dead zones expanding, greenhouse gas emissions from fertilizer production accounting for roughly 2% of global energy consumption. And yet, when simple experiments demonstrate that plants can thrive on natural electrical stimulation, requiring no chemicals and no recurring costs, mainstream agriculture responds with silence. Why aren't universities conducting massive trials? Why aren't government agencies investigating whether this could reduce fertilizer dependency? Why isn't research funding flowing toward understanding and optimizing electroculture? The answer becomes obvious when you follow the money. Agricultural research funding comes primarily from industry partnerships. Major universities receive millions from fertilizer manufacturers, pesticide companies, and agribusiness corporations. These funding sources create powerful incentives to focus on topics that align with industry interests. A researcher proposing to study copper wire electroculture faces significant career risks, skeptical colleagues, difficulty publishing in prestigious journals, challenges securing future funding. The system has made investigating alternatives to chemical inputs professionally hazardous. This pattern repeats throughout history. Established industries resist technologies threatening their business models. Oil companies suppressed electric vehicles for decades. Tobacco companies buried health research. Pharmaceutical giants fight natural alternatives that might reduce drug dependency. When profit depends on perpetual consumption, permanent solutions become threats. So here we are in 2026. Industrial agriculture is doubling down on chemical-intensive methods, developing new, synthetic fertilizers, and building increasingly complex systems requiring expensive technology and ongoing subscriptions. But there's also a growing movement of farmers, researchers, and home gardeners rediscovering these forgotten electrical methods. They're sharing results online, publishing in independent journals, building evidence that's becoming increasingly difficult to dismiss. The internet has changed the game. In Christofleau's era, suppressing information meant controlling a few journals and major newspapers. Today, a farmer in India can share electroculture results with gardeners in California, researchers in Brazil, and activists in Europe instantly. Information spreads faster than industries can contain it. Nearly a century ago, a French farmer proved you could grow extraordinary crops using copper wire and atmospheric energy. Government committees documented it. Patents detailed how to replicate it. Then, the fertilizer industry emerged with a subscription model, guaranteeing perpetual profits, and suddenly this simple solution became inconvenient. The technology was marginalized, dismissed, eventually erased from mainstream agricultural consciousness. But the physics didn't change. The electrical field between sky and earth is still there. Plants still use electrical signals to regulate growth, and copper wire still conducts atmospheric electricity more efficiently than any plant tissue. Today, we have better evidence than Christofleau ever imagined. Chinese researchers documenting 30% yield increases across thousands of hectares. Home gardeners conducting controlled experiments with detailed results. Growing scientific understanding of how electrical stimulation enhances plant biology at the cellular level. The question isn't whether electroculture works anymore. The data increasingly suggests it does. The question is whether we'll allow profit-driven industries to continue dictating what solutions we're allowed to explore. This isn't just about growing bigger tomatoes. It's about who controls how we feed ourselves. It's about whether agriculture must depend on expensive chemical subscriptions, or whether simpler, more sustainable approaches have been deliberately kept from us. The harvest of the future doesn't have to look like the past century. The alternative was discovered 100 years ago, documented, tested, then buried. But it's still here, waiting in old patents and archived photographs, in experiments of curious gardeners and trials of forward-thinking researchers. The energy is still flowing. The copper is still available. The knowledge is still accessible. The only question is, what will you do with it? If you try electroculture in your garden, document everything. Take photos, measure yields, share your results. Real data from real experiments builds knowledge that industries can't suppress. The future of food might be growing in your backyard right now.